It's a regular Sunday afternoon. You sit with your favorite bowl of meal and gulp down the largest bite of food. Wonder what happens next? Let's take a brief look. Chewing combining with the sloshing saliva turns food into a moist lump. It goes down the esophagus all the way to the stomach, where it is left at the mercy of these muscular stomach walls which pound the bolus, breaking it into chunks. Food is now dissolved with acids and enzymes which break down its proteins, and after 3 hours the lump is now a frothy liquid chyme ready to move into the small intestine. The bile secreted from the gallbladder to the duodenum dissolves the fats floating in the slurry of chyme so they can be easily digested by the pancreatic juices. Here comes lipase, flowing with the pancreatic juices that have leached onto the scene and breaks down fat molecules into fatty acids and glycerols for easy absorption into the body and also largely contributing to energy production. Lipase breaks down fats into fatty acids and glycerol and can also be termed as lipid hydrolase. It falls under a class of enzymes called serine hydrolases that catalyze the hydrolysis of amide and ester bonds in proteins and peptides. There are various serine hydrolases just working their way in our body, and lipase is one of them. Serine hydrolases are ubiquitous, spanning all life forms. Now, let's delve deeper into the intricate details of our enzyme's active site.
At the heart of lipase's catalytic power lies a trio of amino acids known as the catalytic triad, which comprises 3 essential amino acids: serine, histidine, and aspartic acid. The triad works harmoniously to facilitate the breakdown of lipids with remarkable efficiency and specificity. Serine acts as a nucleophile and plays a critical role in the catalytic mechanics. Histidine, with its imidazole ring, acts as a general acid-base catalyst, and the aspartic acid provides a stabilizing effect. As the triad's components work together, the enzyme's molecular machinery drives the hydrolysis of triacyl glycerol. Also known as triglyceride, is a lipid that stores energy in the body and is the main component of fat in humans and other vertebrates. The molecule comprises 3 fatty acids attached to a glycerol molecule by ester bonds. Human pancreatic lipase converts triglyceride into monoglyceride and 2 fatty acids. For this catalytic mechanism, we are focusing on just one of the ester bonds here. The problem with serine is, in its alcohol form, they are not good as a nucleophile to attack the ester bonds. It will be activated by protonation from the neighboring histidine amino acid. The alkoxide formed attacks the carbonyl carbon to generate an unstable tetrahedral intermediate. When the tetrahedral intermediate collapses, it forms an acyl enzyme intermediate with the fatty acid and the oxygen of serine. Furthermore, deprotonation of histidine releases a 1,2-diglycerol unit. To do hydrolysis of fatty acid and serine, we will need a molecular water. Histidine will take a proton away from the molecular water, making hydroxide that will attack the carbonyl carbon on the acyl group, forming another tetrahedral intermediate. This tetrahedral intermediate breaks down, releasing free fatty acid and restoring the enzyme's active site. Never mess with a fat-fighting ninja. Lipase is here to break down those greasy fries. Thank you.